So I know folks are still hopping on the call, but in the interest of moving us along and keeping us on schedule, I'm gonna start with introductions. So good afternoon, everyone, and welcome to the first event in this year's Writers Across the Curriculum Speaker Series, hosted by the Writing Center at Michigan State University. My name is Dr. Karen Morosky-Rigney. I'm one of the two associate directors of the Writing Center here at MSU, and I'm very glad to welcome you all to today's event. I'd like to thank the College of Arts and Letters Engaged Pedagogy and Programming Grant Fund for making this series possible, and would also like to thank the following members of our Writing Center team for all their support. Dr. Trixie Long-Smith, our director, Dr. Grace Pregent, my co-associate director, Philip Montgomery, our assistant director, and Orville Cayedito and Nicole Golden, our amazing professional development coordinators. This event would not be possible without all their contributions. I'd like to direct your attention to the email where you received your Zoom link to join us today. In that email, there's information on how to navigate our webinar space. I hope you'll find it helpful. That same information document houses links to materials Dr. Wolfe would like you to access and use during her talk, so you'll want to keep it handy. We can relink it in the chat for expediency's sake. I'd also like to note that today's talk will be recorded so we can share the event asynchronously via our YouTube channel and our website. And lastly, after our time together ends, we will reach out to you again via email with a response survey regarding today's event. This speaker series is the fourth grant-funded speaker series we've hosted here at the Writing Center at MSU. Each year, we've asked ourselves, what questions are urgent in our field? Where should we be learning more? Where should we be investing our energy and our attention? Over time, we've held speaker series on language justice, the work of storytelling, and disability justice. This year's turn toward Tier 2 writing, or writing across the curriculum, or writing in the disciplines, was designed with the urgency we feel as Writing Center practitioners to meet the moment our students and our consulting staff are in today. The pandemic has changed education. It's changed educators, it's changed students, it's changed our starting lines and our points of engagement. These changes require a recursive process of coming to know who our writers are and what they need from us. Because we work with writers from all majors and departments in a Writing Center, this year's speaker series is meant to help us refocus our work and refine our understanding of our shared writing communities. We are very, very excited to welcome Dr. Joanna Wolfe as the opening speaker in this year's series. Dr. Wolfe is teaching professor of English, faculty consultant for mechanical engineering, and the former director of the Global Communication Center at Carnegie Mellon University. Her research focuses on writing and communication in STEM and on equity and communication in engineering teams. Her research has been funded by the National Science Foundation and has received awards from the American Association of Engineering Educators, the IEEE Professional Communication Society, and the National Council for Teachers of English. Her work on engineering communication and equity has appeared in Technical Communication Quarterly, the Journal of Engineering Education, Journal of Business and Technical Communication, IEEE Transactions on Professional Communication, Written Communication, and Sex Roles. She is the author of the textbook Team Writing, A Guide to Working in Groups, and is currently working on a series of genre-based technical communication textbooks for Bedford St. Martin's, tentatively titled Modular Technical and Professional Communication. Dr. Wolfe's work on writers in the sciences improves and expands our understanding of providing support across multiple disciplines. Our Writing Center already uses her work to help inform how we structure consultations for STEM writers, and we feel like there's a celebrity among us to have her here today. Without further delay, I would like to give the virtual floor to Dr. Wolfe to go ahead and get started.
Well, thank you so much for that lovely, lovely introduction. Let me go ahead and share my screen. And hopefully, please speak up if I'm not sharing what I hope to be. I'm going to begin with a short overview of what I hope to discuss today. So going to start by providing an overview of academic writing across the university. And what I really want to do is unsettle any ideas that there might be that there's a universal way of writing across the academy, and to make the case that there are both some broad similarities in the type of thinking that we do, but in terms of some of the more particularistic natures of different disciplines, these are conventions that students need to be taught. Then we're going to move into what do we need to teach students in STEM? And I'm going to start with an inductive exercise to kind of get you thinking, see what you can infer for yourself. Then I'll go over two concepts, IMRAD, which stands for Introduction, Method, Results, and Discussion, and the novelty moves for introducing research in STEM. And then we'll look at some examples of good STEM writing. So let me start first with a study that I conducted in 2015 with Barry Olson and Laura Wilder, where we examined 7 different academic disciplines. And our goal of this study was to see what was similar and different across these disciplines. We looked at the types of arguments writers made, and we looked at examples of both professional and student discourse. We looked at how the writing was organized, and we looked at different stylistic preferences. The disciplines we chose, of these, 4 of them were because they are the most common, most popular undergraduate degrees, and that is psychology, biology, business, and nursing. We chose English because that is where most students learn how to write. And we chose history and engineering to kind of balance out with an additional STEM discipline and an additional humanities discipline. And our first finding was that the types of arguments, the types of thinking that students were asked to do were very similar across all of the disciplines, although the format of that changed. In every discipline we examined, we saw writers identifying some kind of pattern or recurrence or theme and interpreting what that meant. So in text-based disciplines, that might be examples of words, patterns of words, metaphors in English, or themes that might get traced across a literary work. In quantitative disciplines, that would be numbers, a trend that we might notice. Take a large body of data on earthquakes and note a particular trend, particular reoccurrence. In other disciplines, that might be observations, but in all of them, writers looked for trends and then said, what did those trends mean? We also saw evidence of comparison and contrast arguments across every discipline. Now, in some of these, we saw the comparison contrast primarily in professional arguments, so published written academic arguments, and in others, we found it only in student writing. But in all cases, in all disciplines, there was comparison and contrast, where the writer might be comparing and contrasting different medical treatments or different investing strategies or different accounts of the same events and drawing conclusions. And we also saw writers applying a theory to understand an object of study. That theory might be something like in English or history, using Foucault's theory of the panopticon to better understand a text or a historical account. Or it could be a theory about the physical world, such as Hooke's law of elasticity, or an economic theory, or a theory of palliative care. We saw this in every discipline except biology, and I do think that that omission is probably just pointing to the limitations of our sample. I suspect it does go on in biology as well. So across these disciplines, we see writers making similar types of arguments, though using different types of data, different types of raw material out of which to craft that argument. Things become a little more diverse when we start thinking about organizational patterns. So most writers learn to write in English disciplines. That's where first-year writing is usually housed in universities. Students in high school often learn to write in their English classes. And English uses a thesis-first organizational structure. And that is where, at the beginning of the essay, the writer spells out, this is what I'm going to argue, and then spends the rest of the essay supporting that central argument and reaching it again, summarizing it again in the conclusion. We also see evidence of a thesis last organizational pattern in some disciplines, where writers, instead of putting their argument first, put their evidence first, and then use that evidence to make the case that they know what they're talking about, that they have done the research, and only then make conclusions. Now, in STEM disciplines, we see the IMRAD format of organization. That's introduction, method, results, and discussion. And this is the most common organizational pattern used across the university. And it's quite different. It has, and we're going to talk about this, how it's structured. It is something that most students are not taught in their humanities courses. They're typically not taught in the writing courses, and only are introduced to it usually through tacit instruction and trial and error in their STEM or social sciences classes. We also saw in applied disciplines some evidence of problem solution arguments, where there's a problem and then some sort of proposal to solve that problem. So the types of organizational patterns across different disciplines are quite diverse. This diversity grows even larger when we think about stylistic disciplines. And each discipline has their own stylistic preferences that really reflect a lot of the values of their field. So for instance, for citation style, in English we use MLA, or Modern Language Association citation style. And what this citation style foregrounds is authors' names and has lots of conventions for how to quote, lots of rules and guidelines and advice for quotations. History has similarly a lot of apparatus for quoting, for citing things and providing elaborations. In social sciences and sciences, which tend to use APA, psychological association, citation style, what gets foregrounded is year, currency, how recent something is. Authors' names are more minimized. They only use the first initial to avoid implicit bias based on author name. And in more STEM disciplines, such as engineering, the IEEE style or the CBE style in biology is a numbered style, where just a number appears. The author's name isn't even mentioned in the text. It's a very concise way of citing, and it really sends the message that what we care about is the information and not who said it. And this kind of value percolates over into several other stylistic areas. So for instance, direct quotations, which are very common in English and are often a core part of teaching students how to write. Core part is teaching students how to quote effectively. Quotations do not really appear in the social sciences and the STEM disciplines. They're quite rare. And even how faculty evaluate plagiarism differs in these disciplines from how it appears in humanities disciplines. There have been studies asking faculty to rate whether or not things were plagiarism. And faculty in the humanities were a little more strict, a little bit more wanted to see more things cited, more direct quotation than authors in STEM disciplines who are like, oh, well, it doesn't matter how it's said. We just want the information. Disagreement is rarely in STEM disciplines, rarely are authors cited, specific names cited. There is disagreement, but it's less direct, more nuanced, more directed at the field than it is in humanities disciplines. And there's large differences in active and passive voice. Fields and disciplines that foreground people, that are interested in people, tend to use active voice, where we put the person at the center of the sentence and make them the doer of the action. But disciplines and fields of studies that are more thing-based, that are more focused on the world, tend to use passive voice because it doesn't matter as much who did it. So if I want to say the catalytic converter was installed, just passive voice, that's what I want to focus on, is the object, the catalytic converter. I don't care who installed it. So voice changes across disciplines. And so this is really important to keep in mind for our students, because some of the expectations that we might have as students get into their upper level disciplinary classes are things that are different from what they've been exposed to before. And we need to make some of those conventions explicit to them and prepare them. Similarly, English teachers need to also prepare students that they are learning to write a particular way in their classes, and that way of writing might need to change as they move into different contexts. So, what does a STEM writer, a STEM student, need to know in order to write appropriately in their field? I'm going to type in the chat and give you a link to a Google folder. And in there, I'd like you to open up the first file in there. And let me go ahead and I'm going to stop my PowerPoint here. And open this up. So you should see right here this file list, and I'd like you to open the first one. I'm going to give you about 4 minutes for this task to read 2 versions of an executive summary, and then at the end is a link to a short survey. I'm going to stop sharing my screen while you complete the survey. If you have any trouble accessing this, please speak up. I'd like you to read these 2 different versions for the same project, fairly typical project in STEM disciplines, and make a decision about which ones you think is better and why. Oh, okay, we need permission. Good grief. Okay, I'm gonna go ahead and switch. Go ahead and type in the chat rather than me messing around with this here. Go ahead and type in the chat which version you prefer and why, once you've read it. And try not to look at other people's answers. Okay, I'm seeing a very, very strong consensus for B. Few people preferred A, but B is hitting about. Looks like we're at least 90% with B. Reasons are that B is better organized. It's easier to see the results. And here, it's clearer, more concise. Someone said you could just read the first and last sentence and get a good sense of what B is trying to say. And somebody else very helpfully said B better follows the IMRAD format. Okay, and I think that is probably the biggest reason here. So let me go ahead and point out a couple things about B here. And please let me know if you're having trouble seeing my screen. So B begins by introducing the problem that is being solved. And so we want to know what would be a replacement material. Then we have a very brief discussion of the methods, really focusing on what the writer would most want to see. Now, when I craft these assignments, and this isn't an engineering class, I get students to focus on an executive summary written for an executive reader. In engineering, I think this is what they need the most, is to really be focusing on the needs of someone who is going to be reading this in order to make a decision. And so someone who is reading it in order to make a decision doesn't need all of the engineering details, though they do need some. And so we need to know how many materials were compared, what they were rated on, what kind of metrics were used, but not much more. Then we find the results, and the results are really clearly signaled. Our results found. Look at this really strong language. We thus selected a further analysis. So we have these really strong words that tell you where you are in terms of the project. And we learn here at the end, okay, that this is the final result. This was the best selected material. And this is another key point, something that A does not do. We know exactly in B how much mass was reduced, and we know how much cost was, how much the cost increases. If we look at A here, and this is something I was really surprised when I first started working with engineering students. So first of all, with A, okay, we have a little bit of an introduction, but most of this is focused on, I'd say all of this is focused on the methods. It's a very common novice mistake for a writer. They focus on the methods because that's what they spent most of the time doing in the lab. It makes sense, but it's not necessarily what the reader cares about. And we certainly don't need to know in the executive summary what software was used, unless it was a really, important or very central to this. And then here, only here, do we really get to the results in the last sentence. Okay, and all we have is the lowest part mass and only a negligible cost increase. This is something I tell my engineering students. I'm like, this casts doubt on your credibility as an engineer. You need to provide specifics. People expect engineers, they expect scientists to be precise, to be comfortable with factual data. And any decision maker, any executive, CEO is going to understand finances. You want to include the numbers in here. So that is another large advantage that A has, that we have this really clear, exact, and precise statement about why we're going with this particular choice. Okay, then we have a little bit of an explanation here where we move to talking about, all right, we recommend it. It only has a negligible increase on the car as a whole, but we have the exact values. So B is following. It has a good proportion of all of the types of information: introduction, method, results with the focus on the results, because that is what readers most want to know. And then a discussion, a recommendation of what to do with it, along with very precise values and really clear, unambiguous language that helps readers follow along, helps them understand where they are in the document organization. So let me go and give you, if you go, you can go ahead and follow this on my screen, or you can open it up, the second document in here, which is a one-page cheat sheet that my Writing Center developed to help students understand what goes in the different sections. Now, a key thing that oftentimes even advanced writers don't understand is that the abstract should be a document in miniature. And what I mean by that is the abstract should have each of those 4 sections in it. Should have an introduction, should say what was done. It should say what the results are, and that should be the focus of the abstract. And it should usually have if there are clear implications, then that should also be part of the abstract, though that is often cut off. So in the introduction, we make a case for why is this important? What is the question? What is the problem we're trying to solve? And a very clear statement of the research question or the project goal or the research hypothesis. Then the methods, which are usually the least read part, especially by non-experts, uses lots of subheadings to really help people skim and find specific information. Typically, people skip over methods, read the results, and then only go back to the methods when they have a specific question in mind. So we organize methods to have lots of small chunks, lots of headings and subheadings so that you can quickly find a specific piece of information and get out of there. Results, we have this little formula for referring to data, saying what the data shows, what we learn from it, and how we interpret it. And then discussion session tends to follow in many disciplines a kind of common format where it begins by summarizing the main findings and putting them in context with other research, then discussing flaws in the current study, and then using those flaws as a reason to suggest additional research to suggest next steps. If it's an applied discipline, often you'll see an implication or a recommendation in the discussion section. Sometimes that can be also in a separate section. Now, the exact names of these fields can differ in different disciplines. For instance, in chemistry, instead of results or instead of methods, sometimes it's experimental. Sometimes things will see conclusion instead of discussion or implications. So, or there can be additional headings, additional sections in between these, but the overall format is the same. And we often think of this IMRAD format is like an hourglass, where the introduction and discussion are both broad. They both sort of say, here's why we're here, why this matters in the world. And then the method and results is more narrowly focused on what was done in this particular experiment, this particular study. And then the discussion is broad again, saying, why does this matter? How has the world changed? What do we do differently now that we have done this experiment? And IMRAD format is very formulaic. And so sometimes people who come to this from humanities find it very, very restrictive. And it is very restrictive. What the trade-off here is that because it's so restrictive, it really frees up the reader. Readers of this know where to find specific types of information. They can skip and skim around without, and be able to find things very quickly and decide at what level of detail they want to go into each section. So it's very free from the reader format. It's very communal in many ways, because by following the shared structure, we kind of know where to find things. It makes it much easier to digest findings and assimilate them and integrate them with prior knowledge much more quickly than in a more humanities-driven essay, where every essay sort of defines its own structure to a larger, more or less extent. Now I'd like you all to go and in this file, go ahead and open PDF number 3, which is a sample. And what I'd like you to do is I'd like to give you a minute to read through the abstract and go ahead and download it. This will be easier. And mark up where those 4 different sections, introduction, method, results, and discussion, appear in this abstract. You might want to use different color highlighters or just kind of note on your own where these sections begin and end. I'm going to give you 2-ish minutes to do that. Okay, so I'm going to now the goal of this exercise is, because I might mark some things a little bit differently than you did. And as long as we're seeing similar things, because some of these phrases are a little bit ambiguous, as long as we're seeing similar things and we see the same general trajectory, I think we're doing okay. And it doesn't really matter what we label them. But where I mark the introduction of this is probably about through right here. Okay, certainly the first paragraph is setting the stage for why this is important and saying what they do. Then I see the methods, where they get into the methods and the details of what they do. Moving down through this sentence right here, where we have the number of faculty. We could say the key aspects of the contribution is part of the introduction or another section, but then they talk about their data collection methodology and how they analyze the data. Now, one thing I want you guys to notice is that in the introduction, we're in present tense. Okay, we fill this gap. We're saying the current state of knowledge in the introduction, and so that's present tense. Once we move into the more narrow part of the hourglass, the methods and results, the tense tends to change to be more focused on past tense, saying this is what we did, and this is what we learned. Okay. Then we see here that we move into the results here. And again, using some strong language, we discover, we find. Then they talk about a second study that they do and what they find. So clear words, clear verbs, such as find for findings, that really emphasize the results here. And so results occupy the majority of this abstract here. There isn't really a discussion or implication in this particular abstract, and that's because the writing here, the purpose of this study is a little bit more theoretical, a little bit more knowledge building, a little bit less having practical implications. Now I'd like to go through this document and point out some other things, and point out that, and if you have questions about like how your analysis of this differed from mine, we can talk about that in the Q&A. I've zoomed out a little bit. Okay, we can see the IMRAD sections though here pretty clearly, and these are clearly labeled introduction, and this uses the numbered citation or numbered headings. We have related work with 2 subheadings. I consider related work really part of the introductory material because it's establishing the purpose and the background for this study. Then with section 3 here, we move into data collection. This is clearly methodology. And one thing that you should notice, we go through this section, we get smaller chunks, more subheading describing the types of data, the university data. They go on for quite a while because the methodology for how they got all of the passwords for faculty and students at CMU is pretty complex. So working with real data securely, other data sets. Notice how they bold lots of things so that we can quickly find information here. The methodology continues on through the next section with the analytic approach, and they're describing how they build the computational models. Again, lots of subheadings through here so that we can easily kind of skim through this, or we can jump and find particular information in here without having to read every single word. So lots of small chunks of text that are easy to skip and skim. And then we get results here, so clearly labeled. One thing that is very important to note is with all of the figures, and this is part of why I choose this as an example, that and because it's a pretty interesting study, it is possible to understand this result without referring to anything outside of the figure. So it's the percentage of passwords guessed after a given number of guesses. And this is so clearly labeled, very well-designed figure so that we can tell computer sciences were least likely to be guessed. So passwords of computer science, faculty and students were the least likely to be cracked. That's kind of reassuring. That's what we would guess. That's what we would hope. Now, when I first read this study, I was sure that humanities would come out at the worst. So I was really relieved to find humanities is right in the middle. Our passwords aren't the best, but they're not terrible. And so you can have some Schadenfreude business sort of landing at the top as the most guessable passwords. But the point here is like that it's really easy to understand just from this figure, just from the caption, everything we need. Notice for this table up above, look at how long this caption is so that we can understand the table. A common misconception is that Figures and tables should have captions that are just one sentence long, or not even a sentence, just a phrase. And that's actually very often not the case. And the trend is moving towards longer and longer captions so that the text is just supplemental. The text might be, if we can't understand it from just looking at all of the information in the figure and the caption, or if we want some additional material. So if we look at figure 2 here, we can understand this just from reading the figure. Again, we have long caption. And as we go through, it's very easy to understand what is going on. It's just by looking at the pictures and reading the text that accompanies it. And this is the way that we know that scientists actually read, that they will read the title, read the abstract, skim the introduction, go to the results, look at the figures. If there are questions about and difficulty interpreting what is going on in the results, most scientists will jump to the discussion section where we expect to see a summary of what's most important. And then they might jump around to the method section for specific information, finding out how annoying and not annoying were calculated, or they might read the text around describing the figure. And every table and figure that appears in the article should be mentioned and described in long form textual format, as well as have the visual format, so that there's very productive redundancy in this kind of writing. Again, allowing the reader to be freed up. And as we go through here, we end not with the discussion, but with the conclusion, which is pretty typical in computer science, that really tries to summarize the main contributions that this study is making, and summarizing, again, some of the main points and putting it in conversation with other research that has been done on this topic. So this gives you some background on IMRAD, and I find that showing students and walking them through and showing them how to read a model essay that is in the same field, same discipline, usually same topic area as their own, does wonders for improving their writing. Now, I have one other concept that I'd like to very briefly touch upon before I turn this over to Q&A. So if you open up file 4 here, this is called the novelty news. And this is typical of more advanced research in most STEM contexts, most social science contexts, and even in a lot of humanities contexts now. Since this work was first documented by John Swales in the 1980s and got replicated in various textbooks, it's become even more and more standard, even more and more common. And so this is the format, kind of formula that most STEM writers use to introduce their work and show how it is new and worth doing. So first, they explain the significance, why it's important. This can often be as short as one sentence or one paragraph, depending on the needs. In an abstract, it might be one sentence. In an article, in the introductory section, the significance might be a paragraph. It's usually brief, but it's enough to establish context. This helps non-experts follow along a lot, and even experts, it's kind of a reminder of why we're all here, why we care, why we're excited and energized about this topic. Then they describe the status quo. What is the current state of knowledge? If we're doing an experimental study, then that status quo might be what does previous research agree upon? What do we understand? If it is something in a field like engineering or computer science, where we're trying to come up with a better solution, a better algorithm, a better recycling technique, a better machine, Then we would describe what is the current state of the art, what is sort of the most typical way of doing something, and what is the most cutting edge way. And then we find a gap in that, something that is missing, something that's been overlooked or understudied or is unsatisfactory. And so there's some negative language that appears in here. And then we show how our current project, our current research fills that gap. And if this is well done, it should feel really logical and natural to lead up to the current study. Let me turn to page 2, and I'll give you 2 quick examples of this, and then we can look at it very briefly in the article on password guessability that we were just discussing. So the first is a very brief, abstract, introductory, very short introduction to a medical study. And so we begin with 1 sentence statement of significance. The peptic ulcer disease, it's bad. It's characterized by frequent recurrence. So we're persuaded this is worth studying. We have a clear statement of the status quo. Recent studies have suggested that getting rid of this particular bacteria reduces the rate of infection. And we know that this is the status quo because it's 6 citations. And here's an example of this numbered citation style I was talking about earlier. So here we have the status quo, and then we move into the gap. However, interpretation of these results has been complicated because several larger studies did not use control groups. In addition, these studies have not been done on patients with gastric ulcer. So we have this negative language of things that are missing, that haven't been done. If this is done well, you should be able to predict the next sentence without reading it. Okay, by knowing that previous research hasn't used control groups and hasn't studied patients with gastric ulcer, you can predict that this study is going to use control groups and it's going to look at patients with gastric ulcer. So there's a nice tight fit in this introduction. Example 2 here is from a more applied discipline where we're building a new thing, okay, a new technique in order to improve things. So again, we begin with a 1 sentence statement of significance. Okay, plastics are destroying the environment. Okay, very well persuaded of the significance of this. Then the status quo. So traditional petroleum plastic is the most common way, but the most common alternative, or a very promising alternative, is bioplastic. So we have a better solution to the most common thing, and then we have an even more cutting edge solution in the next sentence. One particularly promising bioplastic is PLA, and a definition of what PLA is. So this is cutting edge, status quo. And then we talk about what's missing. However, commercial viability of PLA is limited, again, that negative language, because it is only compostable in industrial facilities and cannot be mixed with other recyclable materials. And again, you should be able to predict what the project is now, because the writer has done such a good job describing the problem that they're solving. Okay? And so to make PLA more commercially viable, notice also this repetition of language here, the commercial viability. This is the problem, this is the solution. And so they're going to build a device that recycles it, that can recycle PLA in a home composting environment. So this is an introduction to a more applied project. If we turn back one last time to this password guessability article here, and we'll just look at the abstract, because the first couple sentences in the abstract very concisely get at these moves. Okay, so we get at here, our status quo is a well-recognized problem. Okay? And so the motivation for studying this problem is that it's poorly understood. So here we kind of in the first two sentences, we see the some of the problems, the properties of passwords. Sorry, my highlighting is being tricky. Is poorly understood. It's an important problem. And then note the next sentence, we fill this gap. So this language of the gap, we see this all over in many of the STEM fields. Well, I'll often also see the novelty of our contribution is. At the introduction here, we again see these moves in a little bit more elaborated context here. So researchers have been studying this problem for decades. The research community has invested in significant efforts. And so the understanding of this field is very important. Then we go into the status quo. We can tell by the number of citations here. But here we get at all of the problems with prior studies, all of the drawbacks here. Small data sets, non-authentic data sets, and all the problems with prior research. And so then we get to, here is our study that is going to fill all of these gaps here. So this is a very common structure for introductions in the sciences. And this is often what makes the difference when we move to more advanced research, to the project that gets the grant, that gets the funding, that gets the recognition, because they are able to explain, and almost invariably using some sort of variation on these novelty moves, able to explain why this project is important and worth doing and really contributes to the state of knowledge in the field. So let me go ahead. I see that I have a couple questions in the Q&A. So let me just take Marilla's question that the figures and tables should be self-explanatory. So yes, they should be self-explanatory as much as possible. I tell writers, unless they are told not to. And so there are people, so a professor, even within the same department, the professor next door could have some different conventions and different expectations than their colleague right down the hall, right next door. So I tell students, if your professor says you need to use short captions, then use short captions. But in general, fields are moving towards having longer and longer captions. And if you look at an article in medicine or in computer science where this one is taken, those fields in particular are going longer and longer captions, more and more information in those, more and more information in the title and in the abstract. And we see some structured abstracts in those disciplines where they explicitly label, here's the introduction, here's the methods, results, and discussion in the abstract itself. So as much information as is needed in the legends, axes, and in the caption for people to understand. Joe asked about guidance about adding hyperlinks to the document. I usually don't have students do hyperlinking in the documents, except for if you do it in Acrobat, if you're using style sheets and styles in Google Docs or Microsoft Word or in Acrobat, those will provide hyperlinks, and I encourage everybody to use style sheets for accessibility format, for accessibility purposes that can help readers jump around and have a table of contents. Let's see. Linking to a specific time within a reference video. If a project requires a video, I think that could be linking to a specific video or specific reference point could be very, very useful. Robert Goldberg says methods must be read almost first because they can be innovative or faulty, making results questionable. Okay, so that's an interesting point. So we know from studies that most scientists, when they're reading a peer-reviewed article, will actually, if they're on a first reading, they will skim over the methods and rely on the peer review process to validate the methods for them. And most read, and so I find that I read very, very differently when I'm reading for my own edification versus when I'm reading as a peer reviewer. When I'm reading as a peer reviewer, absolutely, I look at those methods, I scrutinize it. When I'm reading as a reader, I want to know if the results are worth spending time digging into the methods. And I want to trust my colleagues that they did a good job with that peer review. In the workplace, the executives, the CEOs are not going to read the methods. Now, other engineers will read the methods. So the methods are important, but they have a much more limited readership. And I think students need to know that. But we do have substantial evidence that most readers do skip over methods at first. Okay. Thesis last seems illogical. Is another Q&A. It's not my favorite either, but it's a phenomenon that exists in the world. And it's most common in history. It's also common in other cultures to have thesis last. And the rationale for that, and it does make sense, I just think the reason that I don't like it is because I'm not used to it. The rationale is first you have to show what you're talking about, and then only then are you qualified to draw conclusions. Okay, all right. Let me see. I'm going to stop sharing my screen here. Are there other questions that I have not yet had a chance to answer?
We do have about 2 minutes left for anybody who's got something they would like to ask. We'll sit tight in the possibility that somebody is typing something to submit.
Okay, all right. So Robert Goldberg again, writes the question: sense of evidence differs by field. Yeah, it certainly does. What counts as evidence differs. So, first of all, the type of evidence is very, very different. The quantity of evidence needed. So in literature, if you're trying to make a particular argument about what a text means, you can have very little quantitative evidence. It's more the quality and richness in what you do with that evidence that counts. By contrast, in most of the sciences, we want to have statistical significance. Statistical significance, what's considered significant, differs by field. So in education, for instance, a p-value, sometimes I've seen a p-value as high as 0.10, 0.10 in that field being talked about as marginally significant. Whereas in medicine, where the stakes are much higher. Like if we educate a student wrong, well, they're probably going to survive. If we get something wrong with the medication, obviously that's much more concerning. If we get something wrong with a bridge, we can have a much more major disaster. So sense of evidence definitely differs by field as well. Okay. And I think, oh, have I practiced in a scientific or STEM field? I had a couple years as a computer programmer, and then I started my career trajectory when I became a faculty member. I got a grant to study teamwork in the sciences. I was interested in gender and equity, and then I became slowly aware that we were not servicing our engineering students very, very well in our writing classes. And it also was a challenge. I found that engineering students were some of the hardest students for me to teach because they often would be like, oh, I hate your subject matter. That kind of dared me to teach them. So it's been a very fun challenge to kind of figure out what would make them tick, how I could get them to be like, okay, I still hate writing, but I like the way you teach it. Or, this finally clicked to me and I can understand why writing is important. Okay, thank you for all of your questions, Robert. I can't see you because of how this is set up, but thank you.
And thank you, Joanna. This has been absolutely fabulous. I know folks in the chat have been really enthusiastic. The post-event surveys are all rolling in already and are very enthusiastic as well.
Oh, good. Oh, thank you.
Yeah. So this has been absolutely fantastic. Thank you so much. And I mean, folks, she's a real person out there in the world, so you can always email her questions too, and
Absolutely.
connect across the field. That's the benefit of our digital age. But in the interest of everyone's time, we've reached 2 o'clock, so it's time for us to dismiss. But again, Joanna, thank you so much for spending your afternoon with us. This was fantastic and super beneficial. We can't thank you enough.
Yeah, and I'll just, if Robert's still there, I'll answer his last question, asking about my background. Again, no, I'm not a computer scientist. I became a computer programmer with an English degree. I did it because of my writing skills, actually. I was a computer liaison and became the only person who could get the IT people and the student services people at University College where I worked. To understand each other so that when I started looking for another job, the IT people hired me. I do have an appointment in mechanical engineering now, and I've read lots of work in mechanical engineering, though there's lots of stuff. I can't tell you what's correct or not correct. I can just tell you if it sounds logical or not, or if it's new in the field. I've read enough in there. So, but thank you again for all your engagement. Okay.
Thank you to our very generous audience today. And again, thank you for being generous and answering questions and staying a few minutes over time.
Oh, of course. Thank you so much. Thank you for having me.
Absolutely.
Okay.